Good. Okay. So once again, good evening to everyone. So this is the unit one. So there is a basic principles for electric machines analysis. Okay. So in the previous class, we discussed the couple circuit. So what is a couple? So there is a electric couple as well as the magnetic couple, otherwise the mechanical couple. Then we discussed the simple modeling of electric machines, then analysis of the linear magnetic circuit, and then analysis of the non-linear magnetic circuit. And then we discussed field energy of the magnetic circuit. So in the today's class, we starting with the non-linear magnetic circuit and then energy and co-energy as well as the how we can convert the electrical energy into the mechanical energy. Correct? So these three topic today we will discuss. So starting with the analysis of the non-linear magnetic circuit. Okay. So any idea what is the meaning of non-linear magnetic circuit? Just one minute. Okay. Yes, student. Any idea what is the meaning of non-linear magnetic circuit?
Sir, hello.
Yes.
Sir, there is some noise from Siddhartha, I think.
Just 1 minute. Sir.
I think we need to mute him. Okay, sir, muted.
Okay. Yeah. Yes. So there is a linear and non-linear magnetic circuit. So we can say there is a simple circuit. We can say linear as well as the non-linear magnetic circuit, and already we studied in the mathematical. So we can say the linear equation and non-linear equation. So this subject is the analysis of electric machines. So we have to analysis the linear circuit as well as the non-linear circuit because every system is a non-linear system, correct? So we can say suppose some response is changing, so maybe the voltage is changing. So we can say yes, current is changing because of the resistor is changing. Correct. So we can say 99% system is a non-linear system. There is a practical application. Only 1% system we can say it is a linear system. Otherwise, all the system is a non-linear system which we are using in the practical case. Okay, so how we can represent the non-linear system as well as the linear system? So simple as per mathematical rules. So we can say XY graph. So we can say on the y-axis there is a time, maybe there is a second, and on the y-axis maybe the any amplitude, maybe the function. We can say function, correct? We can say this is a function, and function maybe the voltage, current, and maybe the power. So we can say this line that is your linear line, correct? So we can say this is a figure one. It is your linear graph, correct? correct? So we can say voltage is changing, it means that is a current is changing. So we can say function is nothing but maybe the voltage, maybe the current, maybe the power, maybe the impedance, maybe the reactance, any parameter, maybe the flux, maybe the theta, maybe the psi, any parameter, correct? Maybe the function. So with respect to time, any quantity will change proportionally, then we can say it is a linear function. Then what about the non-linear? So same graph we can plot. So on the x-axis, that is a time, and maybe second unit is a second, and on the y-axis there is a function. So we can say non-linear means there is a not straight line. We can say yes increasing and then is a like this. So this graph we can say it is a non-linear, correct? So we can say figure 2 non-linear graph, correct? So we can say yes function, that function is maybe the time, that function is maybe the voltage, maybe the current, any function. So we can say simple line equation we can say y equal to mx plus c. So this is simple line equation, correct? So we can say y is a output, m x is a input, m is a constant parameter, and c is a constant parameter. Correct. So this is a simple line equation, and we already studied this line equation in the standard 10. Yeah, maybe in the your BTech program. Correct. So we can say y, that is your output, x, that is your input, and c, that is your constant, and m, that is a vary the quantity, and there is a multiply with x. So this is a simple fundamental concept of the linear and non-linear circuit, correct? So now main thing is a magnetic circuit, because this subject is a magnetic, correct? So how we can relevant this non-linear magnetic circuit? Just one minute. Non-linear magnetic circuit. So whenever we can say the non-linear magnetic circuit, then we have to consider the two condition. First one, that is a saturation, and second one, that is we can say economical beta. Otherwise we can say steady state condition. Otherwise we can say economical better, correct? So because our machine is a non-linear device, correct? So we have to consider that this thing, there is a saturation, maybe your machine is saturation, otherwise maybe the steady state condition, otherwise we can say the economical better operation, correct? So whenever we can say the steady state condition, otherwise the economical better, then we have to consider the following situation. Okay. So we can say the hysteresis losses, then eddy current losses. After that, I square R losses. So this type of losses we have to consider while we are designing the any electric motor. Otherwise, we can controlling the any kind of motor. Correct? So as we know, hysteresis losses, that is directly proportional to the frequency, but eddy current losses, that is directly proportional to the frequency, but it is a square of the frequency. Correct? So that hysteresis losses and eddy current losses is most important parameter while calculate the efficiency. So because of these losses, we can say our system is working in the non-linear condition. It is not like linear condition, correct? So with respect to the BH curve, so that is a BH curve, correct? So we can say B versus S, BH curve, correct? So we can say yes. So this is the H, and on the y-axis that is a B, correct? So unit of B, that is a Weber per meter square, and unit of H, that is a ampere per meter, correct? So we can say non-linear curve for BH, it is like this, increasing, and this is constant. So we can say this area there is a non-linear graph of the BH curve, correct? So we can say yes. So B, there is a magnetic flux, and this H, there is a magnetic intensity, correct? So we can say B, there is a magnetic flux density, and unit is a Weber per meter, and H is a, there is a intensity, correct? Magnetic flux intensity. So this BH curve, so we can say figure 3, BH curve for typical silicon steel. Silicon steel used in the electric machines. Correct? So normally we can use the silicon steel to design the electric machine. Sometime maybe the aluminum, sometime maybe the copper. Depend on the type of application where we have to use the electrical machines. Correct? Now, next topic we can say the electromagnetic energy conversion. Electromagnetic energy electromagnetic energy conversion. Because we can say machine is nothing but electromagnetic device, correct? So we can say electrical part as well as the mechanical part, correct? So how we can draw the block diagram of this electromagnetic energy conversion, correct? So this is the most important process, how we can convert the electrical energy into mechanical energy, and mechanical energy into electrical energy, correct? So electrical energy, so we can say the electrical system. Yes, we have an electrical system. Then we can say coupling system. Yes, so this is your coupling system. And after that, we have a third system, that is a mechanical system. Yes, and then entire system we can say there is a electromechanical. So how that is connected? Yes, two-way connection. Maybe electric motor to generator, maybe generator to motor. Correct. So maybe we can say the electrical energy into the mechanical energy, otherwise the mechanical energy into the electrical energy. So this figure we can say there is a step-by-step process for the conversion of the electrical energy into mechanical as well as the mechanical into electrical. So as the electrical system, we can say input parameter, maybe the voltage, maybe the current, and power. correct? And the coupling system, we can say electrical coupling, otherwise mechanical coupling. Correct? So depend on the time response, depend on the system efficiency, we can use the electrical coupling as well as the magnetic coupling. And the mechanical system, we can say output, maybe the torque, yeah, maybe the speed. Correct? So overall figure, we can say process of electromagnetic energy conversion. Okay, so this is the simple flow chart, otherwise simple block diagram of the electromagnetical energy conversion. So we can say yes, electrical system, coupling system, and the mechanical system. Electrical system is nothing but your, that is your input, maybe the input energy, that is your power, correct? Coupling, that is maybe the electrical coupling, maybe the mechanical coupling, okay? And then mechanical system, then output we can say torque and the speed. So this overall process, we can say it is your block diagram of the electromechanical energy conversion system, correct? So this,
Excuse me, sir.
yes,
The topic is electromagnetic, and the thing you explain is electromechanical, I think. Is it the same or different, sir?
it is the same. Electromagnetic and electromechanical both are same,
Okay, sir. Thank you.
because electromechanical is what we have to convert the energy, correct? Suppose you can say electromechanical, so we can consider the maybe the IC engine, correct? So what we are doing, IC engine, so that is your energy, correct? Petrol or diesel, and then we can convert into energy. So that is a simple thing. So ultimately we have to convert the one form of energy to another form energy. But how we can convert? So this is the electrical machines, correct? And machine we can divide in two category. Maybe the motor, yeah, maybe the generator. But ultimately we have to take the output, maybe the electrical output, yeah, maybe the mechanical output, correct? So that's why we can say it is an electromagnetic energy conversion, otherwise electromechanical uh, conversion. Okay, so this is both are same.
Okay, sir.
Okay, yeah, one more question for you, for the student, all of you. We can say electrical coupling and mechanical coupling, which one is better and which one is fast? Any idea? We can say we have a two coupling, there is electrical coupling and mechanical coupling. So which one is a very fast and which one is a slow? Any idea?
Magnetic coupling, sir.
Magnetic coupling is better, yeah, fast?
Fast.
Magnetic coupling is a fast, okay. Magnetic coupling is a fast. What about another student? Other student, which one is the fast? Magnetic or electrical? Why magnetic coupling is fast? Can you justify?
Sir, I think magnetic is
Magnetic.
better because there is no losses, mechanical losses. Mechanical mechanical coupling is fast because it's directly coupled.
There is also friction and other losses, also twisting, bending losses in mechanical coupling.
Okay, so my first question is which coupling is fast, electrically or mechanical?
Magnetic coupling.
Magnetic coupling is fast and electrical coupling
Because
is
the
slower.
yeah, yeah, in my ideas, in my thoughts.
Okay, and what about the losses? What about losses in magnetic coupling and electrical coupling?
In magnetic coupling, sir, there is a two losses, hysteresis and eddy current losses, while circulating fluxes in the core. And electric coupling, there is loss of I square R loss.
Okay. Yes. So there is a magnetic coupling. You said there is a fast, and electrical coupling. You said there is a slower. Correct. But from my point of view, I can say magnetic coupling is a lower. Sorry, slower compared to the electrical coupling. Correct. Why? Because electrical response is very fast compared to the magnetic response. So suppose you want to couple the two things. Maybe I can say yes, I have one device. So device number one and device number two. Suppose I want to couple these both devices. Correct? Suppose I want to couple with these both devices. So I can do the electrical coupling, and you can say the flow of the electron from one device to another device, it is very fast. So coupling of the electrical system is very fast. Correct. And magnetic coupling is lower. Yes, suppose I want to connect the two system, device 1 and device 2. So this is from my point of view. Okay, so maybe I am wrong, but from my point of view I can say it is a magnetic coupling is a slow process, and electric coupling is a very fast process. Okay, so we can say we have to couple. So maybe something like we have to couple. Correct. Yes, losses, you are correct. So losses is high compared to the magnetic, compared to the electrical. So losses is lower in the in the electrical coupling. Correct. So this is the little bit difference, but I am not sure, but maybe you are correct. But from my point of view, I can say magnetic coupling is lower compared to the electrical coupling, and electrical coupling is better compared to the magnetic coupling. Okay. So this is the overall the electromagnetic energy conversion process. Okay. Now I am coming back to the energy relationship. Correct. Yes. This point I will cover next. Now energy relationship. Energy relationship. Correct. So we have a many kind of energy. Correct. We can say co-energy, field energy, energy with load. So how we can represent the energy with the relationship? Correct. So we can draw the block diagram of energy balance. Correct. So we can say block diagram of energy balance. So yes, input. So we can say WE, electrical energy input, WEL, that is the electrical losses. Okay, WEL is nothing but electrical losses. This is WES, is nothing but electrical storage. Correct. Electrical storage energy. So we can say this is your plus, this is losses minus, this is a minus, and this is your output. Output is what? WE, electrical, your input. Correct. Electrical input. So this electrical input is going to coupling system. Correct. So we can say yes, one input. So this is a positive. Losses, WFL, there is a field losses. Losses means there is a negative sign. And WF, field storage energy. Correct. And here there is a mechanical output. Correct. And again we can say there is a summation. We can say mechanical losses W mechanical losses minus mechanical storage, and finally mechanical energy, Wm. So we can say this figure block diagram of the energy balance. Yes. So this WEL, that is your electrical losses. This WE, that's a total electrical energy. Total electrical energy. Correct? This WES, it is your electrical storage energy. By capacitor, otherwise the inductor. Correct? We can store the energy, maybe the capacitor, maybe the inductor. Correct? So we can say C, otherwise the L. What about this WFL? So you can see this is the electrical system. Yeah, after that I will represent. This is the electrical, this is the coupling. So WFL, what? That is a field energy. So this is the field losses, because this is coupling, correct? So we can see the field losses. So this is the field storage energy. Field storage energy, and this is the mechanical energy. So we can say this is the mechanical energy. Yes, this is the mechanical losses, WML, mechanical losses. This is the mechanical storage. And finally, Wm, that is a total mechanical energy. Correct? So this is the notation for this diagram. So we can say this component is nothing but your electrical system. This is nothing but your mechanical system, and this is nothing but your coupling system. Yeah, so you can see we have a electrical input energy, correct? So we have electrical input energy, then losses, electrical losses, as well as the energy storage losses. Yes, we can store the energy by the inductor, by capacitor, correct? Then output, that is electrical energy. So we can say this is the electrical input. Electrical input, correct? So this is the basic energy relationship. We can see the energy relationship block diagram. So block diagram of the energy balance system. So we can say yes, we have an electrical system, we have a mechanical system, and in between we have a coupling, correct? So we can say it is a electromechanical coupling system. Okay. So how we can write the equation for this diagram, correct? So we have to write the equation for this diagram. So we can write, yes, equation number 1, WE equal to WEL plus WE plus WES. So we can write equation, first equation, We electrical energy is equal to We electrical energy plus WEL electrical losses plus WES. Equation number 1. Yes, you can see from this diagram, We is equal to WEL plus WES plus WE. Correct? Otherwise, you can see WE equal to all the input. Correct? So we can write, yes, this equation. Second equation for the mechanical, Wm is equal to Wm plus WMML mechanical losses plus your mechanical storage. Correct? So we can say equation number 2. Yes, any confusion, student? Any query, any confusion for this equation? Okay. If we can define, if WF, there is a field energy, WF is defined as the total energy transferred to the coupling field. Correct? So we can say total energy it is transferred to the coupling field. So we can say WF, that is a field energy, is equal to WF small f plus WFL, that is a losses. So we can say, yes, suppose you can give the 100% input, correct? So that is your field. So you will get the output of field, that is a losses plus your field energy, correct? So we can say this is the field energy and this is your losses. So we can say this is the total field energy. So this is the losses and this is your field energy. Yes, we can say, yes, we have to consider the losses also, correct? Otherwise, we cannot say our system is 100% correct. We don't have a system that is 100% efficiency. Yes, we can say 99% efficiency, 80% efficiency, 98% efficiency, correct? So we can say the electromagnetic energy electromechanical system must obey the law of conversion of energy. Yes, in the beginning of the class, I told you we cannot create the energy and we cannot destroy the energy. We can just convert the energy from one form to another form. Correct? So maybe the electrical energy into mechanical energy, mechanical into electrical, any form. Correct? So finally we can write WF plus WFL is equal to WE minus WEL minus WES plus WM minus WML minus WMS. So this is the part number 1. This is the part number 2. And this is the part number 3. Yes. So this is the field energy. This is the electrical energy. And third part, there is a mechanical energy. So you can see, we can convert. Suppose we have a, suppose we have a electrical energy, then we can easily convert it to mechanical energy by the coupling system. Correct? So this is a simple process and straightforward equation. So we can say this equation number is the 4. Yes, equation number 4. Correct? So from this equation, we can simply write WF, there is a field energy, plus WFL, there is a losses, is equal to WE, electrical energy, plus WM, there is a mechanical energy. Correct? Equation number 5. So we can write field energy is equal to nothing but electrical energy plus mechanical energy. Correct? So this is a simple equation. Otherwise, we can write WF, field energy, is equal to WE plus WM, that is your, suppose you can neglect the losses, then we can write field energy is equal to your electrical energy plus mechanical energy. Correct? Yes. So till now, any confusion, any query? Okay. Okay. Now we move ahead with the detailed analysis. So same topic, that is your energy in the coupling field. Energy in the coupling field. Correct? So we can say the field energy and we can say the co-field energy. So classification, so we can say first one is a field energy and second one is a field co-energy. Yes, any idea? Any student? What is the difference between the field energy and field co-energy? First one is a energy and second one is a co-energy. What is the difference between the energy and co-energy? Any idea? Any student? Yes, anybody? Any idea? Okay. So now I am going to fundamental concept. What is the difference between the active power, reactive power, and the apparent power? So we can say the active power, reactive power, and apparent power. P, Q, and S. What is the difference between the active power, reactive power, and apparent power? Yes, maybe. What is a unit of active power? What is a unit of active power? Yes, student. Anybody? What is a unit of active power?
Watt,
What?
kilowatt, megawatt,
Very good. What is the reactive power?
भार kVAR,
Yeah.
What?
भार kVAR,
KBAR.
KVAR. Okay. We can say the VAR. Correct. Okay. And what about the apparent power?
VA.
VA. Very good. Now just tell me what is the difference, because most of the student you are in the industry and maybe the core electrical domain. Correct. So what is the difference between these three power? Otherwise, where we can use active power, reactive power, and apparent power? Yes, in our house load, we can use all these three powers in apparatus. Maybe suppose you want to run your ceiling fan, correct? Yeah, maybe the tube light. Then we can use this all three power. Yeah, what? Yeah, we can use only one power, that is active power.
No,
Yes,
no, all three powers may be used there, sir.
all three power. Okay. What
Yeah.
about the other student? Okay, your energy meter. So which power is reading?
Active power.
Active power.
Active power.
Okay. Then why you told we can use the all the power? Suppose your energy meter is read only active power, not the reactive power and apparent power. Then how we can use the reactive power and apparent power for the ceiling fan?
Sir, in ceiling fan, there is a the magnetic fluxes inside. So, to magnetize the windings, so reactive power is emitted.
Okay. So any simple example of the active power and reactive power and apparent power? So every time we are using the active power and reactive power and apparent power. Yeah, sometime maybe we are not using the active power and reactive power.
Yeah, yes,
So every time we have to use the active power, reactive power, and apparent power, correct?
not no correct. Not every
No,
time, not every time.
not
But
every time. So which
in
time we have to use?
in case of lighting resistive loads like as heater, so we generally use
Inductive or
active
capacitive
power.
load.
Okay. So I can say inductive load.
And capacitive load.
So suppose we have active load, inductive load and capacitive load, then we can use the three power. Yeah, only one power.
Three powers, sir.
Three power. So we can say P, Q, and S. We have to use, correct? And what
Yes.
about the resistive load?
Only watts.
Only P.
Yes.
Only P. And our energy meter, it is read only the P.
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 So how we can say our load is only resistive load? So suppose you have a ceiling fan, correct? So ceiling fan is a resistive load, yeah, what?
No, inductive load.
Inductive.
Inductive load. But you are saying that this our energy meter is reading only P, that is your active power. How is possible? You got my point? Yeah, no.
Yes, sir.
Yes, sir.
So how it possible? So in Nepal, so you have a what is the cost of the 1 unit in Nepal?
In
Nearly about
domestic single phase 9 to 11 rupees maximum. Single phase
Nine, 9
five.
to 11. That's a Nepali curry, correct?
Yes,
yes.
9 to 11 rupees for single phase. 5 to 30 amperes probably at least.
Okay. Okay. So this is your homework. So you have to identify. So suppose your energy meter is reading only active power, then maybe in your domestic load is all are the resistive load, correct? As per your statement. Suppose energy meter is reading P, Q, and S, correct? Inductive load, capacitive load, correct? Then where we can use the reactive power and apparent power, correct? So I can give this thing for your homework, so you can just think on it, correct? So where we can use the inductive load, capacitive load, and resistive load. Yes, we can use this all three types of load in our domestic application, correct? But suppose we have an energy meter. Yes, every home have one energy meter, that is a separate energy meter. We have to pay the amount for the electricity bill, and we have a three type of power, that is active power, reactive power, and apparent power. Correct. So Suppose we have a three type of power, and as per your statement, energy meter is reading only active power. Then what we can do with the reactive power and apparent power? So that is a free of cost. Yeah, what? Correct. So yes, you can think on that because this thing that is related to that energy and field energy. So field co-energy that is directly related to the reactive power. That is directly related to the reactive power. Any idea what is the reactive power? Any student? Any idea what is the relative power? Reactive power. Sorry. Any idea?
Magnetizing core, sir.
Magnetization core. Yes, 80% correct. So it is a consumable or not consumable.
It
So
is
suppose I have a one. Suppose maybe the 10 VAR power. 10 VAR power. Correct. So we can say Q equal to 10 VAR. And suppose I can say we have a one magnetic circuit, correct? So we can say flux is equal to 10 Weber per meter square. Okay. So I can pass this power 10 VAR to this magnetic field 10 Weber per meter square. So this 10 VAR it is consumed in the 10 Weber per meter square. Yeah, it is just circulating. Any idea?
So it's just circulating, sir.
Just circulating. Then what is the use of
Yes.
this reactive power? Why we need to just circulating? Why it is required?
So for inductive and capacitive load,
Uh-huh.
sometimes the load consumes reactive power. Sometimes the load gives reactive power. So
Yes,
reactive power is always in the line, sir.
yes, good. So, yes, now I got answer. So, one more thing for the more clarity, one more thing. Transformer, right? What is the unit of transformer?
VA
VA, correct? And what is the unit of motor?
kilowatt.
kilowatt. Yes,
Kilowatt,
yes,
otherwise the watt, correct?
Mm,
yes.
mm.
Kilo we can put the K because of the high rating. Otherwise, normal unit is a watt. Why this thing? Transformer unit is a VA and motor rating is a KV, KW. Sorry. Why like this? Again, this concept is related to co-energy and this reactive power. So, did you observe in the industry? So, transformer rating is a VA and motor rating is a W. Did you observe this thing?
Sir,
No. Yes.
sir, just for an example of motor, sir, uh, when motor is operated on low load, the power factor drops very low, and at that time it requires reactive power, more reactive power. But on loaded condition, it power factor is nearly about 0.8 or zero point 0.9. Then it requires standard reactive power. Reactive powers are maybe variable.
Yes, you are correct. So transformer, we don't know which type of load we can connect with the transformer. Maybe the capacitive load, maybe the inductive load, correct? Yeah, maybe the resistive load. That is a depend on the customer, correct? And we know that inductive
Yes,
and capacitive, that is a power factor is 90-degree phase difference, correct? So we can say suppose you have inductive load. So that is a voltage is leading to the current that is a 90-degree. But suppose you have capacitive load, then we can say current is leading to the 90-degree of the voltage, correct? But in the case of the resistive load, so there is a no phase difference. So that's why transformer rating is a kVA, not the watt W. But in the case of the motor, we can supply the electrical power and output is a mechanical power. Then there is no concept of the power factor. That's why we can say electric motor because we are supplying the power and we know there is power factor. There is maybe the point 0.8, maybe the point 0.9 because we are getting the power from the somewhere. That's why we can say it is a unit is a W. Okay. That's why motor rating. Motor is always in the W, because we know the power factor, and output is a mechanical. And whenever we can say mechanical, there is a no concept of the power factor. Correct? So this type of question is most important for the your exam, not exam, that is your centralized exam, otherwise the your state level government exam. Correct? Not for the for master level exam. Correct? So in the simple way, I can say active power, reactive power. Suppose you have a glass. So total volume of this glass, total volume, that is your kVA, and that is your, we can say, the apparent power. So total power, correct? So from the diagram you can see, from this diagram, triangle diagram, we can say active power, otherwise the real power. So you can see, yes, this quantity is a active power, that is a consume, we can consume this thing, correct? Maybe this is any liquid, maybe the juice, yeah, any liquid, maybe the thumbs up, yeah, maybe the Coca-Cola, anything, correct? So we can take this thing, and this is a consumable, so this is the real power. But you can see this gas, correct? So this gas is a reactive power. Without reactive power we cannot store this thing, correct? So this reactive power is most important thing. Without reactive power, we can no store the your active power. So that's why we can say reactive power is most important in the electrical energy. So it is a circulating. Without reactive power, your real power is not consuming. Correct? So we can say reactive power is always circulating in the circuit. It is not consumed. Correct? But we can consume the real power. Whatever drinks it's available in the glass, we can consume this drink, correct? But for the proper storage, for the proper maintain of this drink, we need the reactive power, and that is a gas, correct? So this is a simple example of the active power, reactive power, and the apparent power. Based on this example, I can say there is a energy. So energy is what? Energy. Energy is your real power, and co-energy, that is your reactive power, correct? So this is a simple concept. So your energy, that is your real power, and co-energy, that is your reactive power. Yes, we cannot use the co-energy, but it is a mandatory for the electrical circuit, sorry, not the electrical circuit, for the electromagnetic circuit. Electromagnetic circuit, co-energy is most important. Because we need to develop the flux, correct? We need to develop the flux, correct? Without the co-energy, we cannot create the flux, and flux is a circulating, correct? Because of the reactive power. That's why we can say we can use the three power, that is active power, reactive power, and the apparent power. Active power we can consume, reactive power, that is a circulating, and total power we can say the apparent power. Yes. Now any confusion, any query? Yes, students. So this is the for the today's class. So we can say the linear and non-linear magnetic circuit. In the case of the electric motor, we can say saturation and steady state condition. Then BH curve and electromagnetic energy conversion process. So we can say the electromagnetic energy conversion process. So electrical system, coupling system, and the mechanical system. Correct? Then we discuss the magnetic coupling, correct? Which type of magnetic coupling is good? Maybe the electrical coupling, and maybe the mechanical coupling, correct? Then we discuss block diagram of the energy balance system. So we can say, yes, we have an electrical system, we have a mechanical system, and we have a coupling system, correct? So how we can balance the system? every system have a losses, correct? So this is the few, we can say the equation. This equation is based on this diagram. We can say yes, input energy, there is a total electrical energy. Then we can consider the output is electrical energy plus your losses. Yes. And finally, we discussed the energy in the coupling system. So there is a field energy and the field co-energy. So co-energy is nothing but your, we can say reactive energy. It is a circulating in the circuit, but it is not consuming, correct? And then we discussed the, that is a active power, reactive power, and apparent power. So what is active power, reactive power, and apparent power with the example, correct? So yes, if you have any confusion, any query, then please let me know so we can discuss. Otherwise, we can say, so first unit we completed today. From the next class, I will start with the MATLAB Simulink because it is the most important thing. Okay. So from the next class, I will start with the MATLAB demo. Okay. So how we can use the MATLAB. Just a minute. Yes. Yes, from the next class, I will start the MATLAB demo, okay? And then I will give the one assignment on the MATLAB Simulink, so you can try to implement that assignment in the MATLAB Simulink. So I would request to all, please install the MATLAB Simulink software in your laptop, okay? So you can try to learn the more thing on the MATLAB, okay? Yes, any query, any confusion? So please let me know, otherwise we can